Hi everyone, welcome back. This time we're going to really dig deep into why does the load decrease in a tension test. Now I mentioned earlier that it's not decreasing. Actually, the stress that your part feels increases all the way to failure. Now the load does decrease, but the stress does not. So let's look at that. Now stress is calculated as based on an area, okay? So you have some load, some force, and it's over a cross-sectional area. However, when you neck, let's just imagine for a second that that's the same area right here. The area that matters is the smallest area, because that's where it's about to fail. And even though your load is the same, force is the same, that area is much, much smaller. So maybe it's like a half of the area. Now, for it to be a half would be crazy, but half the area. So what we see here is that as the area decreases, well, our stress is going to increase. Our stress will increase. And so what's happening here at necking is even though in our load seems like it's decreasing, the area is decreasing much faster, and therefore our stress increases all the way up to failure. All the way up to failure. So that is what's going on there. That's why in the tension test you see the load drop, which is just the resistance of the material to being pulled, and why the stress actually does increase. There are ways to calculate this theoretically. There's not a super perfect way to do it though. Okay, ductility. Now we've been mentioning that the more elastic something is, the more it can stretch without failure. Now when we talk about elasticity, we'll talk about something that being ductile. If it is ductile, it means it can stretch a lot. A ductile material can take a whole lot of deformation before it reaches failure. So we're not really thinking about how much stress it's taking. That's called strength. What we're talking about is how far it goes in this direction. That's ductility. Okay, ductile, and then strong would be how high it goes up here. There's actually very technical terms for all these things. Just remember that ductility is how much it can stretch. More brittle materials will have larger Young's moduli because it takes more stress to cause them to deform. More stress to cause them to deform. Like look at it this way, for the same deformation, if my modular elasticity is 10 or 20, we're going to say, let's just say, a crazy thing of being 1. That's insane. That'll be 100% deformation, but we're just going to act like it's okay. Well, then with 10, it'll be 10 stress, and for 20, it'll be 20 stress. So the more modular elasticity increases, the more stress it takes for a material to deform. Okay, and one last little detail to throw in here is that we saw Hooke's law earlier, which was for normal stress. However, we also have the exact same thing for shear stress right here. And that has its own modulus, which is the shear modulus G. Eventually we're going to learn how E and G are connected. There is a connection between the two. But we're not going to worry about that right now. What we're going to do is jump into some example problems. So thanks for paying attention, and if you'll tune in next time, we'll do some examples together. Have a great day. Bye-bye.